Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are opening what is probably the most essential chapter in any engineering handbook.
Hmm.
We're talking about the fundamental laws governing flow, pressure, and thermal transfer.
Mm-hmm.
These are the invisible forces pneumatics, the incredible power density of hydraulics, safe pressure vessel design, and of course, critical thermal management.
Yeah, and this deep dive is really our shortcut past all the introductory definitions. Our
Yeah.
mission here is to take the source material and show you the key, the non-negotiable relationships, the equations that dictate how air compresses, how fluid delivers that mechanical muscle, and crucially, where all the heat goes.
Right.
If you are designing anything that moves or holds pressure or needs cooling, these core physics relationships are, well, they're your foundation.
Absolutely.
Yeah.
So if we're sketching a robotic arm, sizing a massive compressor, or designing a cooling loop for a server bank, these are the physics we just cannot violate. We'll start with the invisible workhorse air and gases, then we'll get into liquid power, move to the safety calculations for air handling and pressurized vessels, and then finish up with thermal dynamics.
Sounds good.
Okay, let's unpack this, starting with the gas law. So pneumatics. It's the study of air and gases under pressure, and it all starts with defining a standard.
A baseline, yeah.
When we talk about standard atmospheric air, we're talking about very specific reference conditions. 32 degrees Fahrenheit and an atmospheric pressure of 14 and 7/10 psi at sea level.
Which you'll also see expressed as 29 and 92 hundredths inches of mercury.
Exactly.
And that standard sets the baseline for the weight of air, which is about 8 and 73 thousandths pounds per cubic foot. But the real insight, the thing that connects it all, is the equation of state.
The foundational relationship.
It's pressure V divided by T equals 53 and 33 hundredths.
Now wait, for the listeners tracking along with the source material, this is a critical moment. In this specific equation, we are not using the units we see every day.
No, you're not.
P here is absolute pressure in pounds per square foot, not pounds per square inch. V is the specific volume per pound of air, and T is absolute temperature in Rankins.
Why are we using pounds per square foot in Rankins here? I mean, isn't that a commonplace for mistakes?
It is the most common beginner mistake.
Yeah.
Mixing up pounds per square inch absolute, ASIA, with the requirement for pounds per square foot, ASV, in this specific gas constant application. The value, that 53 and 33 hundredths, it's derived specifically for the units used in the U.S. standard system.
Okay.
And using Rankins, which is just Fahrenheit plus 459 and 67 hundredths, keeps the math simple because it starts at true zero temperature, which is essential when you're analyzing the volumetric behavior of a gas.
And this is where getting those units right really pays off.
Right.
Understanding compression efficiency. The contrast between adiabatic and isothermal compression is, it's vital for anyone signing off on a massive compressor purchase. Oh, this is a huge financial and physical design decision. Adiabatic compression happens without any heat transfer to or from the air during the process.
Right.
You put the energy in, the pressure goes up, and the temperature just absolutely skyrockets. It's fast, it's inefficient, and it requires robust, large components to handle that heat and pressure surge.
And isothermal compression is the theoretical unicorn.
It is.
It's a compression that happens while transmitting sufficient heat away to maintain a constant temperature.
Precisely. And the physics is clear. The energy requirements for isothermal compression are considerably less than for adiabatic. In the real world, every compressor you design is trying to get as close to isothermal as possible, with cooling jackets, intercoolers, aftercoolers.
So the cooling system can be just as important as the compressor itself.
Oh, yeah. The cooling system often dictates the cost and size of the compressor package just as much as the piston or the scroll mechanisms do.
That's a fantastic transition. If adiabatic compression generates all this massive wasted heat, let's see how efficiently we can transfer power by minimizing waste in the liquid realm. Let's talk about liquid muscle basic hydraulics.
First things first, we need to nail down those pressure notations again.
Right.
We discussed absolute pressure, but most people work with SIG, pounds per square inch gauge. That's just what your local gauge reads above the ambient air pressure.
Right. And SIA absolute is always gauge pressure plus that ambient atmospheric pressure, which we said is usually 14 and 7/10 psi at sea level.
Exactly. So when dealing with hydraulic pumps, the power required to drive it gives us a really clear metric for efficiency. The horsepower is calculated as P multiplied by GPM divided by 1714 times E, where E is the pump's efficiency.
That looks like a bit of a mess of constants, but what's the quick takeaway for a designer? If I'm just starting to spec out a system, what's the rule of thumb?
The quick approximation is incredibly useful, actually. For every 1 unit of horsepower you put in, you can get the equivalent of 1 gallon per minute at 1500 psi.
Wow, that's a powerful metric.
It is. A 20 horsepower unit will comfortably drive 20 GPM at that 1500 psi rating. That kind of power density is why hydraulics just dominates applications like heavy construction equipment or industrial presses.
And the simple payoff of that pressure comes when the fluid acts on a cylinder. The thrust force, T sub F, is just the piston area, A sub 1 multiplied by the pressure, P.
It's direct.
Super direct.
Yeah.
It's the application of pressure right into mechanical work.
And that ties directly into flow speed. The piston speed, S sub P, relates the oil flow, C sub M in cubic inches per minute, directly to the piston area, A.
So you control the speed of the output by controlling the flow rate into the cylinder. Simple as that.
Yep. But the smooth operation of that system depends entirely on how the fluid itself is behaving inside the pipes.
Which brings us to one of the most important dimensionless numbers in engineering.
The Reynolds number.
The Reynolds number. It's the ratio of inertial forces to viscous forces.
It's the physics of what happens when you push thick syrup versus, say, water through a pipe. It's calculated as the product of d, v, and rho, all divided by mu.
So that's pipe diameter, velocity, and density divided by the dynamic viscosity.
You got it.
And this is really the so what moment for any pipe and valve design. We hit a threshold at 2000. If the Reynolds number is less than 2000, you have smooth, predictable, low-loss laminar flow. It's all very orderly.
But if R goes over 4,000, you have fully chaotic, high-loss, unpredictable, turbulent flow.
And that's bad.
Oh, it's very bad. That turbulence causes massive friction losses, erosion, inefficiency. Every designer spends their time trying to keep their system out of that chaotic zone, which usually just means lowering flow speed or increasing the pipe diameter.
And that band between 2000 and 4000, that's the transitional zone. You just don't want to be there.
You don't. And since viscosity is such a major part of this equation, we have to mention the headache of measurement.
Oh, yeah.
We see poise, centipoise, or CP. There's the Krebs unit, which you see a lot in paints, and of course, Seybold Universal.
The variety is a legacy issue, but you have to know which one you're dealing with before you order the fluid or apply any of these equations.
You'll be referencing conversion charts constantly if you work across different industries.
Right. And we should briefly note the Manning equation is used primarily for calculating water flow, especially in open channels, but also in some closed pipes. Okay, now let's pivot sharply from the flow inside the pipes to the containment of that pressure. This is a critical safety component, designing pressurized vessels.
Absolutely.
We've established that internal pressure exerts an equal force per unit area on the walls, but how you calculate the stress depends entirely on the thickness of the metal relative to the diameter.
And that relationship, that dictates safety. We basically have 3 main stress equations. For low pressure, thin-walled cylinders where the wall thickness is small compared to the diameter stress, S, equals the inside diameter multiplied by P divided by 20, where it is wall thickness.
Okay, that's straightforward. But once the pressure rises and the wall thickness becomes significant, the stress distribution changes completely.
It does. For high-pressure, thick-walled cylinders, the simplified equation changes too. Stress, S, equals the outside diameter multiplied by P divided by 2T.
So the reference shifts from the inside to the outside diameter. That's a crucial shift.
It is. And if you're dealing with ultra-high pressure things, something approaching, I don't know, a deep-sea submersible hull or industrial synthesis vessels, you have to move to Lamé's equation.
And that one's much more complex.
Far more complex, because it uses the ratio of the squares of the outside radius, R, and the inside radius, R. It really emphasizes how dramatically stress concentrates near that inner wall at extreme pressures.
And the structural design doesn't stop at the walls. Cylinder ends, they're normally made hemispherical or curved.
Right. And that's done very precisely so that the stress exerted on the ends is equal to or even less than the stress in the cylindrical wall. You eliminate a weak point by distributing the force smoothly.
Exactly. So, moving to industrial environments, let's talk about air handling, the controlled movement of large volumes of air.
Okay.
We all know CFM cubic feet per minute, that's the volume flow rate. But when we talk about forcing air through ductwork, we hit static pressure, FTP.
This is the measure of resistance. It's caused by elbows, filters, registers, anything in the way. And it's measured in inches of water gauge, or WG.
And what's truly fascinating, and often really expensive, is the power relationship here.
Mm-hmm.
Static pressure varies as the square of the flow rate.
Yeah, that's a big one. You double your required flow rate, your static pressure resistance quadruples.
And on the human factor side, we have the SON rating.
Right.
Unlike the decibel scale, which is logarithmic, the SON scale is a linear unit of perceived sound loudness. So if something is rated at 6 SONs, it is perceived as twice as loud as 3 SONs.
Which is invaluable when you are designing a system for, a place where people actually have to work.
Totally. Now let's talk about the infamous air-moving law, commonly known as the Cube law for horsepower.
Ah, yes. This relationship governs how dramatically the required input power increases with flow rate.
This is the equation that catches companies out when they try to retrofit or upgrade ventilation without enough analysis. The new horsepower required is equal to the cube of the ratio of the new flow rate to the existing flow rate multiplied by the existing horsepower.
So why is it cubic?
Right, that dramatic jump.
Because you are fighting friction, velocity, and pressure all at the same time. You're moving a larger mass of air, which is a linear increase. You're moving it faster, that's a squared increase. And you're overcoming exponentially greater resistance, that's static pressure squared.
The power requirement just explodes.
It does.
Let's run the example from the source material because it illustrates this perfectly. Say you have a system moving 7,000 cubic feet per minute, and it runs on a 1-horsepower motor.
Okay.
But your new safety requirements demand you increase the flow to 10,000 cubic feet per minute.
So the ratio of the flows is about 1 in 429 thousandths. When you cube that ratio, the required new horsepower doesn't just go up by 40%, it jumps to 2 in 92 hundredths, so basically 3 horsepower.
Wow.
So simply increasing the flow by about 40% almost triples the power requirement, and it triples the associated energy costs. This is why air handling design needs to be perfect from day one.
And these laws dictate things like industrial air quality standards. For design, a typical office needs an air change every 6 to 12 minutes.
But an industrial environment like a foundry requires a much faster change, say, every 4 to 8 minutes.
So if you have an 800,000 cubic foot foundry and you target a 5-minute air change, you need a system capacity of 160,000 cubic feet per minute.
And that cube law is running in the background of every single one of those calculations.
Which brings us to our final segment, the heat equation. Thermal management is critical because all that power we've just discussed, in the compressors, the hydraulic pumps, the fans, it eventually turns into waste heat.
It has to go somewhere.
Let's start with basic, sensible heat transmission through a surface. The formula is H equals AU times the difference between T sub naught outside temperature and T sub I inside temperature.
Where A is the area and U is the coefficient of heat transmission.
And that U value is where material selection provides the ultimate payoff.
Look at the stark contrast. A single pane window has a U value of 1 in 13 hundredths.
Right.
But 3/4 of an inch of drywall with 3 inches of insulation reduces that U value to a mere 7 hundredths.
That's an order of magnitude difference in heat retention. It just shows the non-negotiable value of proper insulation for energy efficiency.
Absolutely. We also talk about specific heat, which is the amount of heat required to raise a substance's temperature 1 degree compared to water, which has a specific heat of 1.
The formula there is the heat required in B2, or calories, is calculated as WCT, so weight times specific heat times the temperature rise.
Which is why water is so good at carrying heat away.
Exactly. Water is 1.000. Aluminum, which is often used in heat sinks, is only 215 thousandths, and lead is a tiny 31 thousandths.
And that's why you can touch a piece of hot lead much longer than hot aluminum. It just doesn't store the same amount of energy.
All systems lose heat through conduction, convection, and radiation. Let's focus on radiation, the black body effect. This heat loss is heavily dependent on the material's emissivity, which is symbolized by E.
Emissivity is basically the correction factor. A perfect black body. A theoretical object that absorbs all incoming radiation and is the most efficient radiator. At 600 degrees Fahrenheit, it loses 4 watts per square inch.
But if that surface is made of copper with a medium oxide surface, its emissivity factor, E, is only 4/10.
Right. Therefore, the actual radiation loss is 4 multiplied by 4/10, which equals only 1 in 6/10 watts per square inch.
This is why polished metals are used to reflect heat in enclosures, while black or dark surfaces are used on heat sinks to maximize the emission.
Yep. Emissivity dictates whether your system cooks or cools itself.
So let's apply this to the common problem of cooling electronics or mechanical cabinets. If you have an enclosed cabinet with no active cooling, you can approximate the internal temperature rise, delta T.
Mm-hmm.
Delta T is approximately 4 and 800ths multiplied by Q divided by A plus 1 and 1/10. Q is the heat generated in watts, and A is the surface area in square feet.
And consider the real stakes here. A cabinet generating 1,200 watts of heat with a surface area of 55 and 6/10 square feet. The expected temperature rise, delta T, is approximately 90 degrees Fahrenheit.
So if the ambient air is 72 degrees,
The internal temperature shoots up to 162 degrees Fahrenheit. That will cause almost any piece of commercial electronics to fail.
so to save your system, you need a fan. The resulting temperature drop, the new delta T drop, is calculated as 3 and 1/10 multiplied by Q divided by V, where V is the fan flow rate in CFM.
And that leads to a clever design consideration for your fan arrangement. If the air inside your cabinet has a lot of internal resistance, high impedance from densely packed components, you want two smaller fans placed in series. They build up pressure better.
But if the air can flow easily, low impedance.
Then two fans in parallel are better, as they essentially double the flow rate, V, rather than boosting the pressure, SP.
And finally, for anyone dealing with facility cooling, the commercial rating of 1 ton of air conditioning is standardized as 12,000 B2 per hour.
Which is equal to 3 and 5/10 kilowatts. You need that conversion factor when you're integrating facility cooling with your system's heat load Q.
So to wrap it up,
We covered how the relationship between pressure, volume, and temperature dictates compression efficiency and why cooling is the real driver of compressor design.
right, and we walked through how the Reynolds number predicts the chaos of turbulent flow and why all those viscosity units are so varied.
And we finished with thermal transfer, where emissivity and surface area are absolutely critical to preventing catastrophic failure.
And if we connect this all back to that initial safety challenge, we spent time on how high-pressure vessels require the much more complex Lamaze equation for design accuracy. We talked thin walls, thick walls, and ultra-high pressures.
So think about what you are designing to contain or withstand in the most extreme environments, whether it's the hull of a deep-sea submersible under immense external pressure or a composite fuel tank in a high-altitude rocket under high internal pressure. Failure is just not an option.
Right.
So if those pressure equations hold true, consider what unexpected material property becomes the limiting design factor in those environments. Is it density, fracture toughness, or something else entirely? Something for you to mull over.
That is a phenomenal challenge to leave us with. And if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together stays together.